Our next steps then are to really dive in and begin the analysis of the orbit and connecting then the energy associated with this orbit to the key variables so that we can finally obtain that quantization condition that we're looking for. So when we do something like this, you can imagine we're going to get into quite a bit of algebra in just a moment in order to write down relations between momentum and radius, and then we're going to have to solve and tie them back into the energy. So whenever we have a complex piece of algebra like this coming up, it's always very useful to have a plan of attack in mind. And ultimately, remember, we want to solve for the energy of the system in terms of this integer number, which is often called a quantum number. We want to solve for the energy in terms of that quantum number. So if we think about the algebra, what that means algebraically is we want to solve independently both the momentum and the radius in terms of energy, and then substitute in here. Then we will have a single equation relating energy and quantum number, which we then will be able to solve. So our basic plan then is exactly as we've just said, is to solve for P and R in terms of the energy E, and then substitute into the expression up here and solve. So it's always good, as I say, to have such a plan. Okay, so just put a little bubble around our plan, indicate what we're doing. So that's our overall plan, but of course we have to begin with the basic physics that controls the behavior of this orbital system. And I don't think I'm giving too much away when we say clearly we're going to be looking at F equals ma. And in particular, you guys have been doing these types of analyses for a while. We get the most useful information thinking about the corresponding radial components. Now, the force in the radial direction is our Coulomb force, which is Coulomb's constant, times the product of the charges. There's a plus E on the proton and a minus E on the electron. That product gives me an E squared with a minus sign. And then it's divided by the distance squared, because we're now writing down force, not potential energy. And that then must equal m times a. The mass is just the mass of the electron, m. And then the acceleration is the usual centripetal acceleration, which has the value of minus the velocity squared divided by the radius. Now, real quick, one thing we can do, of course, is to cancel out our minus signs, which is very good. And now we're relating velocity and mass to position. And this is very tempting, this combination. Notice I've got mv squared. That's almost exactly kinetic energy. So it would be useful to solve for the kinetic energy, because ultimately I want to relate everything to energy so that I can carry out my plan of attack. So let's start with that. So let's get 1/2 mv squared. And while we're at it, as we know, we want to think in terms of Hamiltonians. So 1/2 mv squared is also just p squared divided by 2m, which will be more useful for us because we want to relate momentum to energies. Now, p squared on 2m is just 1/2 mv squared. To turn this into 1/2 mv squared, I must, on the right, what I've done is I've multiplied by 1/2, and then also multiply by r. That's how I generate 1/2 mv squared. So I have to multiply this by 1/2 of r. So that will give me 1/2 Coulomb's constant times the square of the electron charge. And remember, I have to multiply this by r to get to mv squared. And when I multiply my left-hand side by r, I'm left just with a single value of 1/r. Now, we can begin to relate these quantities to the energy. P squared on 2m, by design, that actually is the kinetic energy. And what I'd like you to notice is that Coulomb's constant E squared over r, that is closely related to the potential energy. I would need a minus sign here, actually, to make this potential energy. I just broke my equality, though, and to restore equality, I would have to put in a minus sign. So you see, we've immediately come to this interesting relation, now proved, which is the related to the virial theorem, which is telling us that in this case, the kinetic energy is actually equal to minus 1/2 the potential energy. And so then we can relate this eventually to the total energy. Now, another way to deal with this would be to write it in the other direction and solve for the potential energy. And the potential energy would then just be minus twice the kinetic energy. The reason why these two relations are so useful is that ultimately we want to get to the total energy E. And the total energy, of course, is the sum of the kinetic and the potential. And there are then two ways we can do this. We can now relate, you see, energy directly to just kinetic or to just potential. And because just kinetic and just potential are related to our variables P and R, we will be able to solve then for P and R in terms of solely the energy. So let's carry this program out. We can start with the kinetic energy version. So for that, what I would do is I would substitute in well, let's go with the kinetic energy. That'll get things in terms of potential. So if I substitute this in for the kinetic energy, the result is I have minus 1/2 V plus V, which of course is just 1/2 the potential. So I've learned that 1/2 the potential energy equals the total energy. So therefore, the potential energy is actually twice the total energy E. But potential, notice, has this interesting relationship to R. So the potential, being minus kc E squared over R, now yields us a direct relationship that we can solve for the radius. So that would tell me, solving this particular relation, I would have to bring radius on top over here, and then bring 2e into my denominator on the other side of the equation. So I'll have Coulomb's constant E squared, and then I have minus 2e on the bottom, like so. Okay, so that gives me the radius R. Now, let's try the other substitution. Let's now write t plus v, but we will use our second equation then to eliminate v from our relations. So this would give me t plus, the potential now is minus 2t. So we learn then that the energy, E, actually equals also just minus the kinetic energy. So therefore, the kinetic energy is equal to minus the total energy, E. And of course, kinetic energy has an interesting relation directly to the momentum. That is equal to P squared divided by 2m. So now we have a second relation that we can use. Previously we had used this one. A second relation that we can use to solve to get one of our fundamental dynamical variables. To solve for P, we just multiply by 2m and take the square root. So the momentum then is going to be equal to the square root of minus 2e times m. And now you can see why I had kind of liked the idea of keeping the minus 2e as a unit here in my denominator. Very good. So we've accomplished our goal. We now have the radius in terms of the energy and the momentum in terms of the energy. So the final part of the plan was then to substitute into the Bohr-Sommerfeld condition. And when we do this, you recall that condition was n times h bar was equal to r times p. And now let's substitute in. So the radius r is this quantity. So that's kc E squared over minus 2e. And the Bohr-Sommerfeld condition, remember, was above. This term then is the radius r. I have to write in also the term that represents the momentum p to do r times p, which is minus 2em. So this is the momentum p. And my final job then is to equate this again to n times h bar, and then solve, this is all nh bar, and then solve this for E. Now to get at E, I think you can see pretty clearly I've got an E in my square root, so I need to square both sides of my equation. So let's carry that out. So I will have Coulomb's constant E squared, because I'm squaring both sides of my equation, divided by minus 2E, quantity squared. And when I square the momentum, that gives me minus 2e times the mass m. And all of this must equal n times, must equal to n h bar squared. H bar quantity squared. Now let's see how we can simplify. One thing that's nice is I've got a factor of minus 2e here, which can cancel exactly one of my factors of minus 2e in my denominator. So now finally you see I can solve for the energy. I'm going to put the energy onto this side of the equation where it will appear on top, and what it will equal is everything that's left on this side of this equation divided by n times h bar squared. So if we can carry that out, I think, in our heads. So the energy again equals everything that's on this side of the equation divided by nh bar squared. So what I have on this side of my equation is I've got, remember this minus sign canceled out, so I have minus 1/2. Might as well get those factors settled. I've got minus 1/2. I have mass. Oh, let's circle it so I know I took care of it. I don't want to lose track of anything important. We also have the mass times the square of the Coulomb terms on top. So mass, Coulomb's constant, E squared, quantity squared. And then there's nothing left on this side other than the energy E, which of course we had decided to move to the other side of the equation. And now I'm dividing by these pieces, which will give me an h bar squared on the bottom. And, ooh, look at that. It also gives me a 1 over n squared. So this is looking very exciting. This is for n equals 1, 2, 3, etc. This is looking very exciting because it's going like minus something over n squared. The big question now is, okay, what is the value of this combination of constants? What is this? Well, we can see it in two places, actually. If we go very much to the beginning of the lecture, because we've been trying to understand all of this, you will recall there actually is, the actual spectrum is minus 1365 divided by n squared. So that looks good if our constants are minus 1365. Now the combination of constants we had far down below should look familiar to us. It's actually exactly what we have here, right? There's the minus sign. There's a 1/2, then there's m times the square of the Coulomb parts divided by h bar squared. Okay, that's a half mass square of Coulomb parts divided by h bar squared. And in fact, that's what we've got. We've got a half, the mass, and then the square of the Coulomb parts divided by h bar squared. So this actually is the 13.65 eV. And we've actually explained then, with this theory, this explains the entire hydrogen energy spectrum. And what's very exciting about this, which I would like to stress, is that notice there's no kind of order of magnitude feel to this, right? There's no arbitrary choices anymore. Choices of, factors of 2, etc. This is a pure, clean prediction that gives us precisely the exact experimental result. That is really exciting. Now, just to tidy up a little bit, notice that this energy is a function of n, this integer number. So, of course, it's nice to label it with the subscript n so we can talk about the different energy values. The other thing I think that is interesting is now that we know the energies of these orbits, the other natural question becomes, okay, what is the actual radius at which this electron would orbit around? Because that tells us then the size of the atom. Now, we did solve for energy, but one of the nice things about this approach is we have a very simple formula that connects radius with energy. So let's implement this formula to find the radius that goes with these discrete energy values. So you'll notice it's simply Coulomb's constant E squared. It's just the Coulomb parts divided by minus twice the energy. So Rn then is going to be I lost it. It's again, the Coulomb parts divided by minus twice the energy. So I've got the Coulomb parts, Coulomb's constant E squared, divided by now minus twice the energy is what goes in the denominator. Here is my energy, right? So minus twice it should be pretty easy to do. Minus twice it will just kill the minus 1/2, and I'm left with all of these remaining factors to copy down. Mass, Coulomb's constant, E squared, right? Divided by h bar squared. Just remember this is the longer line. And then times the 1/n squared factor. Oh, okay. So interesting. Right on top, I've got one factor of the Coulomb factors, which will cancel the two factors I had down there, leaving a 1 on top. I can then just flip the h bar squared, does a double flip to end up on top. So I will just have h bar squared divided by what remains in the denominator is mass times 1 of the Coulomb factors. And then n squared flips up back on top. So that gives me an expression for the radii of the orbits. Now, what is also exciting about this result here is not only to get the radii of the orbits, but I want you to note that for the ground state, that's the lowest energy state, to get the ground state of hydrogen, that would correspond to n equals 1. And we can see that because n equals 1 gives us the most negative number. And when we do that, we find E1 then is minus 13.65, which we said before was the exact ground state. And it is also, of course, what we had estimated from the Heisenberg uncertainty principle, which we just got lucky on in terms of its prefactors. That estimate could have had some slop in it by a factor of 2 either way, and it was just coincidence we matched it exactly. But this matches perfectly. But the other interesting thing is this radius of the ground state should give us really a non-arbitrary evaluation of the size of the hydrogen atom via the size of this particular orbit. And when we look at the value we get for R1, that's of course just this factor here. It's h bar squared over the mass times Coulomb's constant E squared. And what's very exciting about that is that should also look familiar to you. If we go all the way back up again to the Heisenberg, sorry for all the moving back and forth today, but if I go all the way back up to what our Heisenberg estimate was, it was exactly that. Planck's constant squared over the mass times the Coulomb pieces, and it has the numerical value of the known size for the hydrogen atom, 0.529 angstroms, and that is exactly what we've got. Planck's constant squared over the mass times the Coulomb's parts, and so that is a perfect, again, non-adjustable, no fudge factors of 2 flying around, a direct estimate also of the size of the hydrogen atom. So this Bohr-Sommerfeld condition has been very successful for giving us a very nice picture of how the hydrogen atom really should work, and in particular our main goal of understanding its energy spectrum.